Pythagoras Theorem. Pythagoras Theorem. In a right-angled triangle, the square of hypotenuse is equal to the sum of the square of the remaining two sides. Theorem on 30, 60, 90 triangle. If the angles of a triangle are 30 degrees, 60 degrees and 90 degrees, then the side opposite to 30 degrees is half of the hypotenuse and the side opposite to 60 degrees is root 3 upon 2 times the hypotenuse. Proof of theorem on 30, 60, 90 triangle. Given in triangle CAB, angle A equals to 90 degrees, angle B equals to 60 degrees and angle C equals to 30 degrees. To prove AB equals to half BC and AC equals to root 3 upon 2 BC. Construction. Take a point D on ray BA such that AB equals to AD. Join points C and D. Proof. In triangle CDB, AB equals to AD. By construction. Therefore, point A is the midpoint of segment DB. Equation 1 by construction. Also, angle CAB equals to 90 degrees as given. Therefore, segment AC is perpendicular to segment DB. Equation 2 as given. Therefore, from equations 1 and 2, we infer that segment AC is the perpendicular bisector of segment BD, or point C is equidistant from points B and D, according to theorem of perpendicular bisector. Therefore, BC equals to DC. Therefore, in triangle DCB, angle BDC equals to angle DBC, angles opposite to congruent sides. But angle DBC equals to 60 degrees as given. Therefore, angle BDC should also be equal to 60 degrees. Therefore, angle DCB is also equal to 60 degrees, being the remaining angle of triangle DCB. Thus, triangle DCB is an equilateral triangle. Each angle is 60 degrees, as proved above. Therefore, DC equals to BC equals to DB. Equation 3. But AB equals to half DB. Equation 4 by construction. Therefore, from equations 3 and 4, we get AB equals to half BC Equation 5. In right-angled triangle CAB, AC square plus AB square equals to BC square according to Pythagoras Theorem. AB equals to half BC, as angle ACB equals to 30 degrees and AB is the side opposite to 30 degrees. Therefore, AC square plus half BC whole square equals to BC square, replacing AB by half BC. Or AC square plus 1 by 4 BC square equals to BC square. Rearranging the equation, we get AC square equals to BC square minus 1 by 4 BC square. Therefore, AC square equals to 1 minus 1 by 4 BC square. Therefore, AC square equals to 3 by 4 BC square. Taking square root of this equation, we get AC equals to root 3 upon 2 BC. Therefore, AB equals to half BC and AC equals to root 3 upon 2 BC. Hence, the theorem is proved. Converse of theorem of 30, 60, 90 degrees triangle. In a right-angled triangle, if the length of one side is root 3 upon 2 times the hypotenuse, then the measure of the angle opposite to that side is 60 degrees. Theorem on 45, 45, 90 triangle. If the angles of a triangle are 45 degrees, 45 degrees, 90 degrees, then each of the perpendicular side is 1 upon root 2 times the hypotenuse. Given in triangle ABC, angle A equals to angle C, which equals to 45 degrees, and angle B equals to 90 degrees. To prove AB equals to BC equals to 1 upon root 2 AC. Proof: in triangle ABC, angle A equals to angle C, which equals to 45 degrees, as given. Therefore, AB equals to BC. Equation 1 being the sides opposite to congruent angles. In triangle ABC, AC square equals to AB square plus BC square by Pythagoras Theorem equals to AB square plus AB square from equation 1, or AC square equals to 2AB square, or half AC square equals to AB square. By taking square root of the equation, we get 1 upon root 2 AC equals to AB. Equation 2. From equations 1 and 2, we get AB equals to BC equals to 1 upon root 2 AC. Therefore, if the angles of a triangle are 45 degrees, 45 degrees, 90 degrees, then each of the perpendicular sides is 1 upon root 2 times the hypotenuse. Example: quadrilateral PQSN is a trapezium. Segment PQ is parallel to segment NS, and PQ equals to 8 and PN equals to 6 root 2. Find NS. In triangle PTN, angle T equals to 90 degrees. Angle N equals to 45 degrees, as given. Therefore, angle NPT equals to 45 degrees, being the remaining angle of triangle PTN. Thus, triangle PTN is 45, 45, 90 triangle. According to 45, 45, 90 triangle theorem, NT equals to 1 upon root 2 of PN. Putting the values of PN, we get 1 upon root 2 multiplied by 6 root 2, as Pn equals to 6 root 2. Therefore, Nt equals to 6. Equation 1. Nt equals to Pt, sides opposite to congruent angles. Therefore, Nt equals to Pt equals to 6. Equation 2. In quadrilateral PQRT, angle T equals to angle R equals to 90 degrees. Therefore, quadrilateral PQRT is a rectangle, as PT equals to 6 from equation 2 and QR is the opposite side of PT in rectangle PQRT. PT equals to QR equals to 6. As PQ equals to 8 as given, and TR being opposite side of PQ, PQ equals to TR equals to 8. In triangle QRS, angle R equals to 90 degrees and angle S equals to 30 degrees. Therefore, triangle QRS is a 30 degrees, 60 degrees, 90 degrees triangle. QR equals to half QS, being the side opposite to 30 degrees. Therefore, QS equals to 2QR. Putting the values, we get QS equals to 12, RS equals to root 3 upon 2QS, being the side opposite to 60 degrees. Putting the value of QS, we get root 3 upon 2 multiplied by 12. Therefore, RS equals to 6 root 3. Now, NS equals to NT plus TR plus RS. NTRS being one straight line. Keeping the values of NT, TR and RS, we get 6 plus 8 plus 6 root 3. Thus, the value of NS is 14 plus 6 root 3. Similarity in right-angled triangles. In a right-angled triangle, if the perpendicular is drawn from the vertex of the right angle to the hypotenuse, then the triangles on either side of the perpendicular are similar to the original triangle and are also similar to each other. Consider the right-angled triangle ABC. Segment BD is perpendicular to hypotenuse AC. Here, we get two more right-angled triangles, namely triangle ADB and triangle BDC. In triangle ADB and triangle ABC, angle DAB is congruent to angle BAC, being the common angle at vertex A, and angle ADB is congruent to angle ABC, as both are right angles. Therefore, according to AA test of similarity, triangle ADB is similar to triangle ABC. Equation 1. Similarly, in triangle BDC and triangle ABC, angle BCD is congruent to angle ACB, common angle at vertex C. Angle BDC is congruent to angle ABC. Both are right angles. Therefore, according to AA test of similarity, triangle BDC is similar to triangle ABC. Equation 2. From equations 1 and 2, we can conclude that triangle ADB is similar to triangle BDC by property of transitivity. Property of geometric mean. In a right-angled triangle, the length of the perpendicular segment drawn on the hypotenuse from the opposite vertex is the geometric mean of the length of the segments into which the hypotenuse is divided. We have already proved that triangle ADB is similar to triangle BDC. Therefore, AD upon BD equals to BD upon DC. Corresponding sides of similar triangles. Cross multiplying the two sides, we get BD square equals to AD multiplied by DC, or BD equals to root AD multiplied by DC. Thus, the perpendicular BD is the geometric mean of the two segments AD and DC of the hypotenuse AC. Example: E is a point on hypotenuse DF of triangle DFH, such that segment HE is perpendicular to segment DF. Segment EG is perpendicular to segment FH, and segment EK is perpendicular to segment DH. Prove that 1. EG square equals to FG multiplied by EK. 2. EK square equals to DK multiplied by EG. EG is perpendicular to FH and EK is perpendicular to DH. As given, angle H equals to angle G equals to angle K equals to 90 degrees. Angle E equals to 90 degrees. Remaining angle of the quadrilateral. Therefore, quadrilateral EKHG is a rectangle, as it has all angles as right angles. EK equals to GH and EG equals to KH. Equation 1. Being opposite sides of a rectangle. Now, EG is perpendicular to FH. Therefore, according to property of geometric mean, EG square equals to FG multiplied by GH, or EG square equals to FG multiplied by EK, as GH equals to EK. Similarly, EK square equals to DK multiplied by KH. EK is a geometric mean. Therefore, EK square equals to DK multiplied by EG, as KH equals to EG. Pythagoras Theorem. In a right-angled triangle, the square of hypotenuse is equal to the sum of the square of the remaining two sides. Given in triangle ABC, angle ABC equals to 90 degrees. To prove AC square equals to AB square plus BC square. Construction. Draw segment BD perpendicular to hypotenuse AC, getting straight line ADC. Proof. In triangle ABC, segment BD is perpendicular to hypotenuse AC. By construction, Therefore, according to similarity in right-angled triangles, triangle ABC is similar to triangle ADB. Therefore, AB upon AD equals to AC upon AB. Corresponding sides of similar triangles. Cross multiplying the two sides, we get AB square equals to AC multiplied by AD. Equation 1. Similarly, we have triangle ABC similar to triangle BDC. Therefore, BC upon DC equals to AC upon BC. Corresponding sides of similar triangles. Cross multiplying the two sides, we get BC square equals to AC multiplied by DC. Equation 2. Adding equations 1 and 2, we get AB square plus BC square equals to AC multiplied by AD plus AC multiplied by DC, or AC multiplied by AD plus DC, as AD plus DC equals to AC, or AC multiplied by AC equals to AC square. Therefore, AB square plus BC square equals to AC square. Hence, in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the remaining sides. Converse of Pythagoras Theorem. In a triangle, if the square of one side is equal to the sum of the squares of the remaining two sides, then the angle opposite to the first side is a right angle. Example: segment AN and segment CM are the medians of triangle ABC, in which angle B equals to 90 degrees. Prove that for AN square plus CM square equals to 5AC square. In triangle ABC, AC square equals to AB square plus BC square. Equation 1 according to Pythagoras Theorem. In triangle ABN, AN square equals to AB square plus BN square according to Pythagoras Theorem, or AB square plus half BC whole square, as N is the midpoint and BN equals to half BC, or AN square equals to AB square plus 1/4 BC square. Or 4AN square equals to 4AB square plus BC square. Equation 2. In triangle CBM, CM square equals to BC square plus bm square, according to Pythagoras Theorem, equals to bc square plus half ab whole square, as m is the midpoint and bm equals to half ab, or cm square equals to bc square plus 1 by 4 ab square. Therefore, 4cm square equals to 4bc square plus ab square. Equation 3. By adding equations 2 and 3, we get 4an square plus 4cm square equals to 4ab square plus bc square plus 4bc square plus ab square. That equals to 5ab square plus bc square. Taking values from equation 1, we get 4an square plus cm square equals to 5ac square. Thus proved. Applications of Pythagoras Theorem. 1. In an acute angled triangle ABC, if segment AD is perpendicular to side BC and angle B is less than 90 degrees, then AC square equals to AB square plus BC square minus 2BC BD. Proof. In right-angled triangle ABD, AB square equals to AD square plus BD square. Equation 1 according to Pythagoras Theorem. Also, in right-angled triangle ADC, AC square equals to AD square plus DC square by Pythagoras Theorem. Replacing DC by BC minus BD, we get AD square plus BC minus BD whole square, BDC being a straight line. Comparing BC minus BD whole square to A minus B whole square, we get AD square plus BC square minus 2BC BD plus BD square. By rearranging this equation, we get equals to AD square plus BD square plus BC square minus 2BC BD. AD square plus BD square plus BC square minus 2BC BD. Replacing AD square plus BD square with AB square from equation 1, we get AB square plus BC square minus 2BC BD. Thus, AC square equals to AB square plus BC square minus 2BC BD. Thus proved. 2. In an obtuse angled triangle ABC given in figure, angle B is greater than 90 degrees. If segment AD is perpendicular to side BC and DBC is a straight line, then AC square equals to AB square plus BC square plus 2BC BD. Proof. In right-angled triangle ADB, AB square equals to AD square plus DB square. Equation 1 according to Pythagoras Theorem. In right-angled triangle ADC, AC square equals to AD square plus DC square. According to Pythagoras Theorem, replacing DC by DB plus BC as DBC is a straight line, we get AD square plus DB plus BC whole square. Equating DB plus BC whole square to A plus B whole square, we get AD square plus DB square plus 2BC DB plus BC square. Rearranging the equation, we get AD square plus DB square plus BC square plus 2BC DB, AD square plus DB square plus BC square plus 2BC DB. Replacing AD square plus DB square by AB square, from equation 1 we get AB square plus BC square plus 2BC BD. Thus, AC square equals to AB square plus BC square plus 2BC BD. Thus proved. Appollonius Theorem. This theorem explains the relation of the length of the median of a triangle to the length of its sides. In triangle ABC, if segment AD is the median, that is, D is the midpoint of side BC, then AB square plus AC square equals to 2AD square plus 2BD square. Proof of Appollonius Theorem. Here we shall prove this theorem for an acute angled triangle using the applications of Pythagoras Theorem learnt. Given in triangle ABC, segment AD is the median. To prove, AB square plus AC square equals to 2AD square plus 2BD square. Construction. Draw segment AE perpendicular to side BC, getting a straight line BEDC. Proof. In triangle ABD, angle ADB is less than 90 degrees. According to first application of Pythagoras Theorem, we get AB square equals to AD square plus BD square minus 2BD DE. Equation 1. Now, in triangle ADC, angle ADC is greater than 90 degrees. Therefore, AC square equals to AD square plus DC square plus 2DC DE. According to second application of Pythagoras Theorem. Substituting BD for DC as BD equals to DC given, we get AD square plus BD square plus 2BD DE. Equation 2. By adding equations 1 and 2, we get AB square plus AC square equals to 2AD square plus 2BD square. Thus proved. Example. In triangle PQR, M is the midpoint of side QR. If PQ equals to 11, PR equals to 17, and QR equals to 12, find PM. In triangle PQR, segment PM is the median. Therefore, QM equals to MR equals to half of QR. Putting the value of QR from the question, we get half multiplied by 12 equals to 6. Now, by Appollonius Theorem, PQ square plus PR square equals to 2PM square plus 2QM square. Putting the values in this equation, we get 11 square plus 17 square equals to 2PM square plus twice of 6 square. 121 plus 289 equals to 2PM square plus 2 multiplied by 36. 410 equals to 2PM square plus 72. 410 minus 72 equals to 2PM square. 338 equals to 2PM square. Or PM square equals to 169. Therefore, PM equals to root 169 equals to 13. Therefore, PM equals to 13.